No, it is. It was off.
We might need to put that back, of course. There we go. Take a minute. Maybe if you close the blind, it might help. Don't know. No, it's okay. It's bright enough, I think. It's bright enough. Okay, so like I said, now we're on to a new chapter, electricity. What? Whose side? You were all telling me that it was your favourite last time, weren't you?
No.
Yeah. But that's what I heard. Okay, physics, electricity, not as big as mechanics, as you can see. Mechanics was what, 28 topics? Whereas electricity is only 11.
Yeah, that's way worse.
Now just have an open mind. Have an open mind. Okay. Charge and current is what we'll start with in electricity. So if you can write that down, please. Charge and current. So since we're at the start of a new chapter, it will start quite easy. Got that? Charge and current?
I and Q.
Yeah. Or rather, Q and I.
Oh.
I know. Right, continue. Right, so from chemistry, or even just basic middle school science, you might remember that electric charge is a basic property of electrons. Electrons have an electric charge. So do protons and other particles. And you also might remember from chemistry that electrons are negatively charged and protons are positively charged. So things that are negatively charged and things that are positively charged attract each other. This makes electrons and protons stick together. Things that have the same charge push each other away. They repel each other. This is called the law of charges. Simply put, like charges repel, opposite or unlike charges. Which do you say in chemistry? Unlike or opposite?
Opposite.
So opposite charges attract. Like charges repel. But you would have done this in chemistry, right? So, tell me this. Electrons are negative, protons are positive. So that's why electrons orbit protons. What's a helium atom made of?
Electron, proton.
How many of each?
One.
One what? Give me words.
One plus one electron.
Think carefully. I said
2
helium.
electrons, 2 protons.
Helium. That's after hydrogen.
2 electrons.
Yes, 2 electrons and 2 protons. Yeah?
He.
Yeah. You've done helium in chemistry, right? Yeah. So if electrons stick to protons because electrons are negative and protons are positive, then why do protons stick to protons if they're both positive?
No one ever told us why.
You'll find out.
Semester
2. If electrons stick to protons because the electrons are negative and protons are positive, then why do protons stick together? Why can helium have 2 protons stuck together if they're the same charge? No?
Because the nucleus, I think there's something on the nucleus that puts like...
Is it something to do with the neutrons?
What is the something?
Is it something to do with the neutrons?
So, magnetic field.
The electrons are pushing them in the middle with...
Electrons are supposed to be attracting them.
Yeah, the electrons should be pulling them out from the middle.
But then they're surrounding them, so they're kind of like...
Anyways, no. You'll find out in semester 2.
Can I try?
Go on.
Is it because they're two masses, so they have a gravitational force
No.
between them?
Nice try, but not this reason. Okay. So I just thought I'd leave that on a cliffhanger, and you can find out next season what happens. So definition, an electric current is just a flow of electric charge. That's all a current is. So in a metal, well, we'll get to that in a moment. So a current is a flow of electric charge. Have we got everybody? No, neither. Yeah. Do you know where he is?
No.
Okay. Continue. So you know also from chemistry that in a metal it's free electrons that flow. You've done that in chemistry. So this is what carries the charge. Electrons move through the metal. So it's just a picture to help you visualize. An electrolyte is a chemical that conducts electricity. So it's a bit like, you know, in chemistry you have conductors and insulators, and metals are conductors, and a current can travel through the conductor. An electrolyte is a chemical, usually a liquid, that allows electric current to travel through it. So it's like it's a conductor as well, but it's a chemical, a liquid. So it's actually what's used in batteries. And it's not electrons that flow, but ions. And you've studied ions, of course, in chemistry. So ions can be both positive and negative. Ions are just, well, if you didn't know it, ions are just atoms with extra or missing electrons, therefore making it negative or positive. And here's an example here of an electrolyte, H2SO4. I don't know if you've done this. Yeah, you've done this one in chemistry? Not this year, but you've done it before. So you can see there's the SO4 ion and the zinc ion, and you can see basically there's a flow of positive zinc to the right and negative, what's that, sulfur, SO4, sulfuric acid, to the left. Anyway, this is not really concerning us because this is more chemistry than physics right now. I just want you to know that an electrolyte is a chemical that allows a current to flow through it. And a good example of an electrolyte is H2SO4. Is a good example. So if you can just even write down what an electrolyte is, you only need this much. So if you can write that definition down. You wrote it down? Okay. Did you write this down, Faisal? Okay. Continuing. Continue? What part are you at?
The yes or the no?
You didn't see her shake her head, so it was a no. Are we just waiting for Furon?
No.
I'm done.
I'm done.
Okay. Which way should we say the current flows? So imagine here
The old
you have
way or the new way?
we have a simple diagram here: a light bulb, a switch, and a battery, AA battery. So do we say, and now I don't think you can see it here, but you probably know from using batteries, this side has a positive sign on it, and this side has a negative. So do we say it flows, the current is flowing from positive to negative, or maybe it's from negative to positive? Or both, or neither. What do we say? Which way should we say the current flows?
I
Positive.
think both.
Positive and negative.
That's the new.
Positive and negative.
Which is it?
Me.
Positive and negative.
So the answer is both. Yes. So let's be clear why it's both. What's happening here, unfortunately, is that we say the electrons, now please listen very carefully, we say the electrons flow from negative to positive. Electron flow. However, we say the current flows positive to negative. You might be saying, well, if the electrons flow from negative to positive, why do we say the current flows from positive to negative? Before an explanation of that, I'd like you to make note of this. So the current is positive to negative, and the electron flow is negative to positive. Got that? Yeah? Okay. Continue. Yes?
You have to draw.
Or just write it down. Okay. So just to be super clear, if an electron moves from A to B, we say there's a current flowing from B to A. That's right, B to A, even though the electron moves from A to B. Got that? Okay. So you might be wondering, why, for the love of all that's good, why? So you can thank Benjamin Franklin for this. If you don't know Benjamin Franklin, he liked to fly kites in thunderstorms. You know the story?
And never get electrocuted.
I doubt the story's true. I would not recommend flying a kite in a thunderstorm. But anyways, Benjamin Franklin was really the first person to study charge. And unfortunately, it was just bad luck. What he called, it doesn't actually matter if you call electron negative or positive, or proton negative or positive. For example, this hand here is left and this one here is right. If I swap the names and everybody swaps the names, there's no difference in anything. You know, if I start calling this one right and this one left, nothing really changes. As long as everybody makes the same change. So if we called electrons positive and protons negative, then that would be okay as long as everybody does that. You see, the only reason we call them positive and negative is to show that one is the opposite of the other. Not because it really is positive and it really is negative, but because one is one thing and the other is the opposite. That's why we call them plus and minus. Unfortunately, just really bad luck, Benjamin Franklin called in his experiment what he thought, or what charge he had left from the experiment, he called that the negative charge, which turned out to be the electrons, which is why we call electrons negative. It would have been better if he just called that the positive charge and called the other one the negative, because it meant we wouldn't have this situation. So because we call electrons negative and protons positive, it would have been better the other way, but it's too late now and it's stuck. Electrons are the negative ones and protons are the positive ones. Maybe one day we'll swap the names. I doubt that would happen, but it would be much better if the other way around. So unless you can travel through time, there's no way of changing this. It's just the way it was set up from the beginning. Okay, so next... What? What? You read the comic?
Yes.
I just thought it was funny when I saw it. Yeah. So Benjamin Franklin, you can look him up anyways. I don't know, he's American, and like I said, he liked to fly kites in thunderstorms and try and capture the electricity in a jar on a key, like charge the key. Yeah. I really don't know if that story's true. It doesn't feel like it could be true.
Who did that died?
Yes.
That's what we know.
Yes.
So did he survive? No one knows.
Or he didn't actually do it.
Maybe he had a glove on or something.
I doubt that, because you got to remember, people didn't understand electricity at the time, so he wouldn't have known what to do.
Even if he wears a glove, electricity from the cloud will burn him and the glove.
If he won't toasted Benjamin Franklin, well done. Okay, so now on to some units. This is a unit maybe you've heard of before. Faisal, please. I'm so tired. So tired. I can't believe it's only Thursday and the break was last week. I feel like I've been back a month.
I need some of my energy.
Yeah. X-Man style, is it? Right, so units. The amp. Have you heard of amps before? Yeah. So the amp is a measure of current, and the definition of an amp is a very, very technical definition. You have 1 amp if you have this much force between 2 straight wires conducting an amp, carrying an amp. I want to draw it before I explain it. So imagine we have 1 wire here and 1 wire here, and there's a current here and a current here, and if they're both the same charge, negative electrons, if they're both the same charge, should there be a force pulling them together or pushing them apart? Yeah, there'd be a very small force pushing them apart. Okay? Can you see? Because, you know, if this is negative and this is negative, they'll want to separate because they're opposite charges. If the force here that you need to apply to hold it in place, so like a sort of cancelling force, you know, to push it back, if that's equal to 2 times 10 to the minus 7 newtons, then you say you have 1 amp and 1 amp of current. So like I said, it's a very unusual definition. This is the definition of an amp. The good news is they don't usually ask this definition in the exam because it's quite a complicated definition. But it's still on the syllabus, it's still on the course, and you still need to write it down. So this is the technical definition of 1 amp of current. If you can write this down, please. Oh, and I forgot to also say in my picture, you place these wires 1 meter apart as well. Yeah, all of it. Huh?
That's a lot of distance.
It is, yeah.
To measure them. Like, if we put them closer, we can measure the force.
I know, it's only a technical definition, not a practical definition. Yeah. What for? What's up? What? Why are you in such a good mood? What?
Produce an attractive force or a repulsive force? We said they're getting repelled.
Yeah, it's just the way I drew the picture. Will produce. I suppose it depends which way you have your currents going. I think the technical definition has them going opposite, which means maybe they attract. I don't remember. I know how I can fix this. Just delete the word.
Produce a force.
Yeah. I'll just delete it until I get the exact picture. I don't think I have a picture, do I? I do. So.
Yeah, same direction, it's attraction.
See it though? Whatever. I'll have to go to Wikipedia later.
We were told in EAP classes to never trust Wikipedia. Ever.
Yeah, you. Not me though. Because I'm able to discern between what is good and what is bad. You are not as developed or mature to do this.
Very,
So it's a repelling force, not
In my picture, I think I have to. In this picture, the currents are going in the same direction.
yeah, but for the example, for us, for the
You know what? I'm going to Google it now in a second because I want to know. I can't remember which way. I feel like it should be repelling because it's the same.
why do you have stream on this?
Because actually, I have one game that works on it. Because it's a game that my friend made. So we studied maths together.
What's it called?
Super hexagon.
No, similar. I was thinking of the shapes that fall down.
Tetris.
Yeah, Tetris.
I think this can run Tetris. Yeah. Let me just check here. Get the definition of 1 amp exactly right.
Can't you just write unit of electric current? That's what I used to do.
Yeah, but that means nothing though.
Ampere current per second.
No, we don't use that definition in this course. I'm looking for there it is. The amp is the constant current which, if maintained in 2 straight parallel conductors, would produce between these conductors a force. Yeah, so it doesn't say attractive or repulsive. It just says a force. So we'll just, I think it's repulsive. I don't know why I typed attractive, but in the definition it doesn't even say if it's attractive or repulsive. So you can just delete the word then.
Maybe they have a picture. If you scroll down.
Maybe they have a picture.
Maybe, yes.
Hey, that's the picture I'm using. There's an attractive or repulsive force. Okay.
Yeah, I think it depends on
The direction, yeah. The force is used in the form definition, which states that the amp's constant current will produce that attractive force. Yeah, okay, so I'm happy enough, I guess. If they're traveling in the same direction, it will attract, and in opposite directions, it will repel. Is that okay? Or if you're unhappy with both, just delete the word attractive and say a force. Okay, do you have this? Now the Coulomb. The Coulomb, which is the symbol C, by Sol, is the International System of Units measurement of electric charge. So what is the definition of a Coulomb of charge? It's the charge you get when 1 amp runs for 1 second. So mathematically, the charge is equal to the current multiplied by the time, where Q is the total charge, I is the current, and T is the time. We'll talk more about what a Coulomb is now in a second, but this is the definition of a Coulomb. This definition they ask a lot in the exam, unlike the last definition. Yeah, I know. Fuang. International System of Units is a proper noun. Unit is a noun. You know, here, I know what I'll do to explain this. This here
Is a fat cat.
is a cat. This is a cat. Fat cat. This is fat cat. And this here, small cat.
Fat kitten.
Fat kitten, yeah. And this is a cat here. Okay, so this cat owns this cat.
Woody.
Yeah. So you would say this is the fat cat. Don't distract me. Fat cat's cat. This is a proper noun and this is noun. His name is Mr. Fat Cat.
And her name is
No, this is just a cat. I thought, do you get my grammar point here? This is a proper noun and this is a noun. That's why I can have the two words together here. Yes? So, Fuan, this international system of units is the name of a organization, a business.
Oh, it means the international system of units is a group.
Yes, yes.
The unit.
Is their unit. Yes, yes. See, you are becoming an expert at English.
Because of you.
Oh, no, because of the cat. Okay, you got this?
Is that an I or an O?
That's an I. I is what we use for current. Capital I.
No, it's IRL.
He just asked me that. Please answer.
When it's too far, I can't hear.
Okay. I. Yes. Alright, so, how big is 1 Coulomb? Well, it's actually a pretty big unit. You've dealt with electrons in chemistry. What is the unit of charge of an electron in chemistry? What do you say the charge of an electron is? Yeah, -1. And a proton? +1, yeah. We don't use that unit. We use Coulomb. 1 electron has a charge of -1.6 times 10 to the -19 coulombs. So our unit of charge in physics is much smaller than what you use in chemistry. This is often just written as E, or really I should rather say -E. No, I think it's E actually. I have to check on the calculator. Or, quote, -1, like in chemistry. And likewise, the proton has the same charge except with a plus, and you know it's +1 in chemistry, but it's 1.6 times 10 to the -19. So anyways, what you need to know is how big of a charge does an electron have. It has this much charge. So you should note that, please. This is also a constant on your calculator. So it's built into the calculator,
What would we need to know?
the number.
So that's a number for 1 Coulomb.
No, for 1 electron.
The size?
Yeah, how much charge it has.
-1.6.
-1.6.
-E.
What number constant?
-E. Because
It's a plus, okay. It should be a -8. Okay. What constant number is it on the calculator? It's on your lid.
23.
23? Okay, let me show you that. So, on your calculator, who has the Casio calculator? Do you see on the lid, there's a list of constants. Constant. Oh, I will when I resave it. Constants on the lid, there's a list of about 40 constants or something, is it? E is somewhere in the middle, 23, is it? So let me show you how to get that.
Shift 7.
Yeah, shift 7, 23. Can you get it on the calculator? Shift 7 and then 23.
The thing is not negative.
Yeah, so I need to write a minus E actually here. Minus E is equal to this.
So the charge in an electron is 1.6.
No, it's minus 1.6, which is minus E on the calculator.
23. Shift 7 and then 23. Shift 7, 20.
Did you get the E on the calculator?
We have to add the negative.
Yeah,
All the time.
for an electron, and for a proton, you leave it like that. Look, where's my cursor? Oh, here it is. Shift 7, 23. That's for a proton. Then if I just stick a minus in front of it, that's for an electron. Okay? Let's have a look at this one. I've only given you one formula today for this first lesson. Charge equals current multiplied time. Q equals IT. Can you use that formula to get the answer here, please? A 100 milliamp current is flowing through a copper wire for 2 seconds. What is the charge over the 2 seconds?
0.2.
Yeah.
Yes.
0. Minus 2.
Your answer is?
0.3.
You've given me 3 answers now.
0.2.
Let's see.
The centi is minus 2. Maybe it's minus 2.
Yeah, Q equals IT. I is 200 milli, correct? Wasn't it, or would I say it was 100 milli? 100 milliamps, and the time was 2. So this is 200 times 10 to the minus 3. So if you said 2, it's wrong, yeah. So the answer is 200 milli coulombs. Or what? Or 0.2 coulombs, correct.
We don't write the sign.
What sign?
Coulombs.
What sign is that?
That's resistance.
What?
Yeah, the resistance.
This is Coulomb sign. See?
No.
Yes, I
No,
know.
I'm replying to 100.
Oh, are you thinking of this one?
Yeah, that's all. Resistance only.
What is that?
Resistance, ohms.
Yeah, no, I'm not saying this one.
Then what one?
Not sure.
You have some special Coulomb symbol?
My phone's out of charge.
Could you go back to the question?
Yeah. I guess I'll find out tomorrow.
Yeah.
Okay. Don't be shocked if I forget to remind you.
That's why I'm asking you.
Okay, continue. So, very simple. Only one formula today, and very simple questions. 5 minutes and you'll be done. They're very easy. I'll go grab your results, and then when I come back, I'll give them to you discreetly. But